This presentation showcases the simultaneous growth of two transitional instabilities in an unsteady airfoil stall simulation. These results are from unsteady, wall-resolved large eddy simulations of an airfoil pitched up at a Reynolds number of 60,000 in the incompressible regime. The visualization is presented in airfoil reference coordinates. As the airfoil pitches up, 2D Tolmian-Schlichting or TS waves develop in the laminar flow near the leading edge. Flow separates from the surface, forming a shear layer akin to a free shear layer in that it has an inflectional velocity profile that undergoes a Kelvin-Helmholtz type instability. In addition, viscous TS instabilities develop in the separated flow beneath the shear layer within a laminar separation bubble. This offers an alternate path to transition to turbulence. The video presentation shows the 3D airfoil suction surface with isosurfaces of the Q criterion representing regions of high vorticity. The isosurfaces are colored by values of span-wise vorticity. On the side, contours of span-wise vorticity averaged across the span are shown. The distribution of the pressure coefficient Cp over the airfoil suction surface, colored by the adverse pressure gradient, is shown at the top. The video begins at the instance when the airfoil has pitched up to an alpha, where a separated shear layer is established at the leading edge and undergoes a Kelvin-Helmholtz instability at the rear of the airfoil, shedding vortices which are convected downstream. They develop span-wise fluctuations and transition to turbulence downstream. Near the leading edge, the laminar separation bubble is beginning to develop. Let's watch the next few instances as the airfoil continues to pitch up. At this instance, the separation bubble has formed as indicated by the region of constant Cp. The bubble reattaches laminarly with the shear layer separating again downstream of it. This can be seen from the slight dip in the shear layer shown by the arrow. The laminar reattachment of the bubble makes it more susceptible to disturbances. Almost immediately after the bubble is formed, large viscous TS instabilities begin to develop at the rear of the bubble. Simultaneously, the Kelvin-Helmholtz instabilities in the shear layer are also amplified, as seen from the appearance of vortex cores in the Q criterion isosurfaces. The next few instances show the simultaneous growth of both instabilities. Typically, unsteady stall cases exhibit dominance of one instability mode over the other, rather than the concurrent growth of both. The initial Kelvin-Helmholtz instabilities occur progressively upstream, but give way to viscous instabilities, which lead to complete transition to turbulence. Alternately, the KH instabilities grow before viscous instabilities grow at the leading edge, but the shear layer vortices are shed as soon as the viscous instabilities begin to grow. In contrast, the current results highlight their simultaneous growth for a specific combination of Reynolds number and pitch rate. The interaction between these two modes and consequent influence on the onset of unsteady stall requires further exploration. The vortices originating from the bubble navigate a region of large adverse pressure gradient and rapidly transition to turbulence. They also have a faster convection speed relative to the shear layer vortices. A stable, turbulent leading edge vortex develops after flow fully transitions near the leading edge.